Right, so we're moving on to electricity, and what we're going to do first of all is recap some of the stuff that you did in Year 7, just to make sure that's sort of settled in your heads, and it'll really help us moving forward with the rest of the topic. Okay, so we're going to start with current, and the first thing to say, or the important thing to say about current, is that it's the flow of charge. Okay, so it's the flow of charge. The actual charge that's flowing are electrons, and they are negatively charged. So they're what's moving along the metal wires, which we'll come to in a second, but current is a flow of charge. And the size of a current, how large it is in terms of a value, is basically telling us how quickly that charge is moving. So if we have a high value for our current, then we know that the charge is moving very fast. And if we have a low value for our current, we know it's moving more slowly. When you made circuits in Year 7, you would have measured the current, and you would have used something called an ammeter. So an ammeter would have been the device that you used to measure the current, and then when you gave a value, when you had a value for current, the unit it would have had was amps, and we would have represented that with a capital A. Something you would have almost certainly done even before secondary school is about the fact that electricity flows through things that we call conductors. So if something's a good conductor of electricity, that means the electricity can flow through it relatively easily. And if something is a poor conductor of electricity, we call that an insulator. So something that we know to be good conductors of electricity are metals. Okay, so metals make good conductors of electricity. So I want you to just pause the video in a second, have a think about some actual examples of conductors that you know, and then also try and think of some examples of insulators. I'm going to write some possibilities in a second, but if you just want to pause the video and have a think yourselves, that'd be great. Okay, so I'm going to start with copper. And the reason I've done that is, well, firstly, it's a metal, and we've already said that metals are good conductors of electricity. But actually, copper is a particularly good conductor of electricity. And all of the wires, electrical wires in your house, all of the electrical wires in the school, etc., they will all be made of copper, and so copper is really the main metal that we use in electrical wires. I've also written iron and steel, two sort of very common metals that we, in our everyday lives, but really any metal that you write is essentially a good conductor of electricity. For insulators, the three that I've decided to choose are plastic, rubber and wood. There are many others as well. And of course, plastic isn't a specific substance. There are a whole range of plastics. If you think of all of the wires, though, that that come out of the plug or go into the back of a computer or, get into your phone, you notice they're all covered in plastic. And so we have the copper wire underneath that plastic, but because we want to protect ourselves, because we've got to be safe, we use an insulator around them, we use plastic around them. So you find all of these wires tend to be covered with an insulator like plastic. Rubber is a good insulator, and so is wood. So they're just some examples of things that don't conduct electricity terribly well. So potential difference. So you might not have had it referred to as potential difference before, I'm not sure. You possibly will have known it as voltage, but we're going to be calling it potential difference. And essentially this is the force that the cell or battery or power supply that we're using, it's the force that applies a force, that does work on the charge. Remember, we've done work done before in the energy topic. So if work done is taking place, then energy is being transferred to the charge. So essentially, potential difference is a measure of the energy per unit charge. Okay. We use a voltmeter, so you've probably used one of those in the past. And of course, the unit of potential difference is volts, and we use the capital letter V. So if we're going to increase the voltage, then we're increasing the force, which means we're going to do even more work on the charge. If we do even more work on the charge, then they have more even more greater energy per unit charge. So the charge is going to flow faster, and if it's flowing faster, there's going to be a greater current. So if you increase the voltage, you increase the current. And one way that you can do that is to add more cells. So if you add more cells, you get a greater current. And if you have a greater current, if you've got a bulb, say, for example, in a circuit, one of the things that you would notice is that you would get a brighter bulb. Now, resistance is a measure of how hard it is for the charge to move. So the unit that we use for that, this is a slightly more unusual sounding one, is ohms. Now, there are components where we can vary the resistance, and if we're able to vary the resistance, well, that allows us to do is control the current. So we can increase or decrease the current if we're able to increase or decrease the resistance. We'll look at that relationship later on. Now, bulbs themselves, or lamps, they have a lot of resistance. They are effectively resistors. So what happens there is the current works really hard to get through. And in doing so, it transfers a lot of energy to the metal that is at the sort of center of the bulb, as it were, or the filament that we sometimes talk about. And that just gets hotter and hotter because more energy is being transferred. And if you think about metals, if you heat them up enough, they start to glow. And that is exactly what's happening really in our bulb. And then it glows, it gets so hot, it glows so much that light is produced. That's an energy transfer, so there's an energy transfer out to the surroundings. So if we increase the resistance, we make it harder for charge to move. Therefore, it moves more slowly. Therefore, it's a smaller current. So if we add more bulbs, if we increase the number of bulbs, we are increasing the resistance because bulbs are essentially resistors. If we increase the resistance, that means less current. So each of those bulbs is going to shine less brightly. They're going to be dimmer. So we're just giving ourselves some of the background information, and then we're going to apply it, and then hopefully it's going to make even more sense. Again, in previously, hopefully you've done symbols of electrical components, so how you represent, say, the cell or a battery or a lamp or whatever, an open switch. And that's something that's really important. It's like a key, it's like a language. It makes life a lot easier because we can see on a diagram exactly what's being represented. So I want you to pause the video again in a second. I want you to have a look at this list of components, and I'd like you to think before I fill it in about what the actual symbols for each of these might be. So pause the video, just jot some down on a piece of paper. There'll be many that you've never seen before, but I'm hoping that there'll be quite a few that you remember. Okay, so pause the video now, and then I'll complete it myself. Okay, so some of them are a little bit shaky, really. It's quite difficult to do on the iPad in a nice sort of smooth straight line, but hopefully you get the general idea. What I'll make sure I do is that I send you a list of like correctly, properly, perfectly drawn symbols, but these are essentially what you've got to be able to know for the rest of the topic. Just a couple of things to point out. So you'll notice that what you might have thought of as a battery, something that, if you were just using what you would call a battery and you had one of those, we're going to be treating that as a cell, and that a battery is more than one cell. Okay, so we've got more than one cell to have a battery. So they're most of the symbols that we need to know, and we're going to start using some of them in subsequent slides. Okay, so we've got two setups on the left-hand side that we could have done ourselves. So they're sort of representing the actual equipment that we would use, what it would actually look like. So we've got what we would have thought of as a battery there, and we've got what we would have thought of as two batteries here, and we've got a lamp or a bulb, and we've got two lamps and two bulbs. So I'm just going to draw how we would represent that using the symbols. So just before I start, we're going to represent the wires with straight lines. So we always draw the wires as straight lines. So when you see it, hopefully mine are fairly straight, but they're certainly supposed to be very straight. So I'm just going to draw now the circuit diagrams to represent those two types of circuit that we've got there on the left. So there's the first. What we thought was a battery is really only one cell, and then our bulb is drawn there. So, and they are supposed to be very, very smooth straight lines. So apologies that they're not perfect. So if I look now at the second one, we can see that I've drawn two cells. So now we in fact have a battery, or that's how we can describe it in the sort of topic of electricity. And I've got two bulbs drawn there as well. Okay, so that's how we would represent those two circuits. So we said earlier that if we increase the number of cells, then we increase the force on the electrons and we increase the energy that's transferred to those electrons. So there's a greater current, and if we have a greater current, then a bulb is going to be brighter, and that's what we're really showing here. So we're assuming that both of these bulbs are exactly the same type of bulb, so they're exactly the same type of resistance. In the first one, we've got one cell, and we've got a bulb that is obviously shining. In the second one, we've got two cells, and we've got a bulb that's shining more brightly. Okay, so more cells, brighter the bulb. This time, what we're changing isn't the number of cells. We're keeping it at one cell, but we are changing the number of bulbs. And again, I'm going to assume that each of these bulbs are all the same type of bulb. They're all like sort of essentially identical. So remember, bulbs were essentially resistors. So if we increase the number of bulbs, we increase the resistance. And then if we increase the resistance, that means there is a smaller current, and the charge doesn't flow so quickly. So we get then a change, or a difference, sorry, in how bright those bulbs are. So in the first one, we've clearly got a brighter bulb than we've got in the second, which does have two bulbs, but they are relative to the first one. In the first circuit, they are less bright, and that's because we have increased the resistance. Okay, so we're just going to put that knowledge into effect in this sort of set of questions here. So we've got 9 different circuits with different proportions, or different numbers, sorry, of cells and bulbs. We've got a series of questions. So in which circuit has the brightest bulb? Which circuit has the dimmest bulbs? Which of them would have the same brightness? So we're going to assume each cell is equivalent, and we're going to assume each bulb is equivalent. And then what else have we got? In which circuit is the current the highest, and in which circuit is the current the lowest? So I'd like you to just pause the video in a second. I'd like you to think about those questions. I would like you to make your predictions, or give your answers, write them down on a bit of paper, and then we'll go through them one by one. So just before I go through my answers, one of the things I'm just going to do is I'm just going to write on each circuit. I'm going to think about this ratios in terms of ratios of cells to bulbs. So I'm just going to make a note on each circuit about how many cells there are in each, and how many bulbs there are each, and I'm going to think of them as ratios to each other. Okay, and I think that's going to help us answer the questions that we've got. So I'm just going to do that now. So that's what I've done. I've just made a note of the ratio of cells to bulbs, so that's green to yellow. So the first question asks us which circuit has the brightest bulbs. So it's going to be the one with the highest ratio of cells to bulbs, which is clearly circuit C. We have 3 cells and 1 bulb, and there isn't anything that gets close to that, or matches that, I should say, or beats it. Which circuit has the dimmest bulbs? So that's going to be where we have the fewest cells, or the smallest cells to bulbs ratio, which is clearly circuit G, because we've got 1 cell to 3 bulbs. In which 3 circuits are all the bulbs the same brightness? So for them to be the same brightness, they're going to have the same ratio of cells to bulbs, and we're going to go for simplest ratios. So if we look at A, E and I, we can see that they are all essentially 1 to 1. So for every 1 bulb there's 1 cell. In which circuit is the current the highest? Well, remember, higher current means brighter bulb, so wherever the bulb is brightest, whichever circuit has the brightest bulb, sorry, that must have the highest current. So the circuit with the highest current has got to be C, and then similarly the circuit with the dimmest bulb is going to be the one with the lowest current, so that is going to be G. Okay, so hopefully that makes sense, but do sort of send me an email or something, or put it in the Google Doc if there's something you're not quite sure about. So we've had a recap of how we hopefully understood current, potential difference, and resistance from year 7, but we do need to have very clear definitions now. So that's what we're going to just write. We're just going to write very clear definitions for current, potential difference, and resistance. Okay, so current is the rate of flow of charge, and something to just really emphasize here is this word rate, because that's telling us how quickly, rate is all about how quickly something changes. So the bigger the current, the faster the rate of the flow of the charge. So that rate is very important. If we look now at potential difference, so potential difference is the work done, and remember work done is an energy transfer, so we can think of it as energy. The work done, or the energy per unit charge. And then finally, resistance is a measure of how hard it is for the charge to move. So please just think about those three descriptions. Okay, so circuits can fall into two different types. We can either describe them as a series circuit or a parallel circuit. To decide which, what we do is we're focusing on how many loops or paths there are for the current to flow along. So in a series circuit, there is only one loop or path, and in a parallel circuit, there is more than one loop or path. So if we look at the example on the left, if we think about what the path actually could be, it's along the wire, through the bulbs, along back through the wire, and then through the cell. So there is only one loop or path on the one on the right, and the one on the left. Let's see what happens if we follow the wires there. So we get to this bulb here, and we have a choice. We could either go through the bulb and then all the way back to the cell and through the cell, or I'm just going to use a different colour to show that the fact that there's a second path or a second loop, we could go through the other bulb like that. So there is a difference. So I'm now going to draw them as circuit diagrams, so we can hopefully see even more clearly the fact that we have one loop or path on the one on the left and more than one loop or path for the circuit on the right. So sorry for the slightly shoddy drawings there, but if we just focus with the circuit on the left, if I just follow it round, highlighting it, you can see there's only one loop, there's only one path I can take. If I look at the one on the right, I could get to this point here, and then I have a decision to make. So I'm going to take one of the paths, and just to show you that there was a possibility of a second path, I'm just going to use a different colour. You can see I could do a different loop. So we can see that there's only one loop or path for the circuit on the left, and there's more than one loop or path for the circuit on the right. Okay, so this is just a little exercise for you to try and identify or spot series or parallel circuits. So there's a variety of circuits here. What I'd like you to do is just get a piece of paper, just write a little subheading series, just write another subheading parallel, and write the letters for those circuits that you think are examples of series circuits, and write the letters for those that you think are examples of parallel circuits. So pause the video, and then you'll see on the next slide the answers, but just pause the video now. So these are the answers. So just to confirm that the ones on the left are series, they should only have one loop, and if I just show those loops, show that there are no other options. So that's for A. For B, okay, going round again, there are no possible other paths. C, okay, again just one single loop. F, right, so you might have been caught out by F. Perhaps it was slightly unfair. We're going to talk about a voltmeter and how it affects or doesn't affect a circuit as to whether it's series or parallel shortly. And then if we look at D, there is only one path. So I appreciate F might have caught you out, and obviously I need to explain that a little bit more than I have already, and we'll do that shortly. Looking at the ones on the right to show their parallel, so I'm just going to draw, that's one possible loop for I, and then another possible loop, could have taken that, so that route round there. Look at G, oh my goodness, so one possible loop, another possible loop, not the best there, sorry about that, and then another possible loop. So actually there were three paths or three loops for G. For E, a bit more straightforward, that's one, and that's a second. And then for H, much clearer. It sort of goes to show how drawing conventional diagrams, circuit diagrams, actually makes life a lot easier. We have a very clear loop there, and we've got a second loop here. So hopefully you're convinced now that, or you can understand or appreciate how you might spot that something was a series circuit or parallel circuit based on the number of loops or paths there are. So we're going to shortly look at differences between series and parallel circuits in terms of things like current and potential difference. So just before we do that, I just need to make a couple of things clear. So we've already said right at the beginning when we were recapping that we measured currents using an ammeter. And whenever you're measuring current, you always put the ammeter in series. Okay, so you're always putting it in the same loop as the components that you want to measure. Potential difference is different. We said earlier that we needed to use a voltmeter, but you always have to put the voltmeter in parallel, so that's in its own loop, for whichever component you want to measure. So the diagram on the right, we are essentially measuring the potential difference across the bulb. Okay, so we're measuring the potential difference from, if you want to call it A and you want to call it B, that's where we're measuring the potential difference. That the voltmeter always has to be in parallel, but this is still a series circuit because as far as the components are concerned, other than the voltmeter, so as far as the bulb and the cells are concerned, they are all in one continuous loop. So if all the other components other than the voltmeter are in one loop, or there's only one path, then that's still a series circuit. So adding a voltmeter which is in parallel does not make the circuit in itself a parallel circuit. So we're now going to consider current, potential difference and resistance, those three key aspects of electric circuits. We're going to think of them and how they are affected based on whether the circuit is a series circuit or a parallel circuit. So starting first with current, one thing to say or one thing to pay attention to is that in a series circuit the current is the same all the way around the circuit. It doesn't matter where you put the ammeter, you will always measure the same current if it's a series circuit. So we have got examples here where we put the ammeter before the bulbs, in between, and afterwards, and it didn't matter, or doesn't matter where we put them, we will get the same reading each time, in which in this particular example it's 0.3 amps. So in a series circuit the current is the same through every component, and it would be the same value wherever you measured it in the series circuit. Now one problem with series circuits is that if you break that circuit at any point anywhere, then the current will stop flowing, full stop, completely. So everything will stop working. So that was used to be like a common problem with Christmas lights. So here we've got a set of Christmas lights in a sense at the bottom. So there is just one loop. If I just follow this around, it's one path, one loop. If any of these bulbs breaks, I don't know, let's say number 2 broke, then all of the bulbs would stop working. So if there's a break anywhere in a series circuit, the current cannot flow. Okay, so potential difference. So remember, it was the cell or the battery or the power supply that provided the potential difference. So we always connect cells in the same direction. So you'll notice that it's the long line in this particular example at the bottom. We have long line and then the short line, and long line and then the short line. So that says they're all pointing in the same direction. If we were to say which was the positive side and which was the negative, it is the positive is always the longer one, negative shorter, positive, negative. So you can see they're all sort of pointing in the same direction. If you've got more than one cell, then the total potential difference will be the potential difference of each of those individual cells added up together. So the cells that we have at the bottom here, they're all 2 volts, and so they all add up together to give a total potential difference of 6 volts. So the total potential difference will be supplied by the cell, battery, power supply, but when we consider the components around the circuit, actually the potential difference is shared between those components. So we have an example here where the power supply or the battery or cell is giving us a potential difference of 12 volts. So when we measure the potential difference just around that cell, so that's, if we're measuring it between A and B here, that will be a value of 12 volts. But if we measure the potential difference in this particular circuit around each bulb, and one thing to say here is that in this example the bulbs are all identical, and that's very important. That's how we can know that that the potential difference is shared equally in this example here. We can see that each bulb has a potential difference around it of 4 volts. So if we just look at that, that's 4 volts. And we're just measuring it when we're using that voltmeter there. That V1 is measuring it between A and B. So they're all the same type of bulb here, so they each have 4 volts between them, or around them, sorry. If we just, let's get a different colour, if we just added those potential differences together that we have in around these bulbs, we would get 12, which is the total that we have around the cell at the top. When it comes to resistance, hopefully this isn't a surprise, particularly given how increasing bulbs and what effect that had on the current. If you want the total resistance in a circuit, you're going to have to add the resistance of each component. So let's say resistor 1 here had a value of 2 ohms, and resistor 2 had a value of 4 ohms. Then the total resistance in this example would be the sum of those 2 values. So in a series circuit, it's the total of all of the resistors put together. So here it would be 6 ohms. Okay, so how are things different when it comes to parallel circuits? So we're actually going to start with potential difference. So what we discover is that the potential difference across each component in a parallel circuit is the same. So what that means is, if I had a value of 12 volts around my cell, if I look at those 2 bulbs which are in parallel, they're in a parallel circuit, we've got 2 loops, and both of them would read 12 volts. Okay, so the potential difference isn't being shared. Each component has the same potential difference, and it's the same as we have around the original cell. However, it's different when it comes to current. In a series circuit, the current was the same all the way. It didn't matter which part of the circuit you were on, it was the same. However, here the current does split. It splits into different branches. So in the example that we've got on the right here, the total current is 18 amps. And then what happens is it splits off into branches. Now again, in this particular example, every bulb is the same, or every bulb is equivalent. That's really important for our examples here. We're making life a little bit simpler. We're making sure that that's like a control variable, right? To have all of the lamps the same is like a control variable. So after the first split, after the first sort of branch, 6 of it has gone down across, on the sort of first loop, 12 of it has carried on. And then when we get to the next branch, that 12 splits also, and 6 of it will go along the second loop, and 6 will go on the third loop. If we were to add another ammeter, I don't know, if we added it here, then our reading, that's at the end of the loop, that's when all of the branches have come back together. That ammeter there would read 18 amps. Okay, so it's sort of like they've come back together. So the total current is the sum of the currents through all of the separate components. So our separate components here were the 3 bulbs. Each of them has 6 amps running through them, so the total is 6 plus 6 plus 6, so that's 18. The current splits into the branches. The total current would flow through the battery or the cell. And basically, the lower the resistance, if these bulbs were different, the lower the resistance would mean a higher current was flowing through them. But that's really something for a later day. Oh, the other thing just to point out though is we could have included switches. So let's imagine there was a switch here, basically a switch on each loop, separate loop. What that would allow us to do is to switch each of those bulbs on and off separately. So actually this is a very common circuit in houses and other areas, because it gives us a lot more flexibility in terms of what we switch on and switch off. So as you can see at the bottom there, different branches can be turned on and off separately. Okay, so that's a very important property of parallel circuits. Now, this is a really curious property. Whereas in series circuits, the total resistance was the sum of all of the resistance in the circuit of each component. Here we get something quite different. Basically, the total resistance here, or the total resistance in a parallel circuit, is less than the resistance of the smallest individual resistor. So if we look at this example that we've got in front of us, we've got a resistor. R1 is 2 ohms, R2 is 3 ohms, R3 is 4 ohms. The total resistance is going to be less than 2 ohms. Okay, so it's less than the smallest individual resistor. So to summarize, in a series circuit, the current is the same wherever you are in the circuit. Whether you're at the beginning, the middle, or the end, the current will stay the same. Whereas in a parallel circuit, what we discover is the current splits. So when you've got a choice between which path to follow, some of the current will go down one path, some of the current will go down the other. How much goes down each will depend on the resistance of the components along each separate path. If we consider voltage in a series circuit, the voltage is splits, or it's shared between each different component, whereas on a parallel circuit, the voltage is the same for each loop. When we come to resistance, in a series circuit, you add all of the resistors up and to get a total, whereas in a parallel circuit, bizarrely, the more resistors there are, the lower the total resistance, and the total resistance will always be less than the smallest individual resistor. And then finally, if you have any break in a series circuit, so if one of those components breaks, the whole circuit stops. There can be no more flow of charge. The path, the loop, it's broken, and if you have no path or loop, you can't have your flow of charge. Your current cannot flow. Whereas in a parallel circuit, each branch can be turned on and off separately, so you get a lot more flexibility with a parallel circuit. Okay, so there are 3 equations in Year 9 that we need to understand when it comes to electricity. They are relevant to what we've been doing, so they're not just sort of abstract equations. This first one basically relates to 3 key ideas that we've looked at in circuits. That's potential difference, current, and resistance. So V equals IR, so potential difference equals current times resistance. We've got our triangle there up in the left so that we can easily rearrange it if we need to. But what I'm just going to do, just to try and hopefully make this a little easier, I'm just going to color code different things so that when it comes to the questions, maybe it becomes a little bit easier to see what we're doing. So I'm just going to make potential difference red for this. I'm going to make current blue. I'm going to make resistance green. So if I look at the first question, it tells me a current of 0.015 amps. And the other thing that I have a numerical value for is resistance. So I have 2.0 ohms. So I'm having to work out my potential difference. So fortunately, I don't need to rearrange that V equals IR because it's the potential difference I want to find out, and that's the subject of the equation that we start with. So V is the subject there. So I know that V is going to equal 0.015 times 2, and that gives me an answer of 0.03 volts. That does actually remind me something I should have just made clear, although we have covered these units before, so I'll have to make sure I do it later. Potential difference is in volts, current is in amps, and resistance is in ohms. Okay. So look at the second question. I am given a current again, so that's an amp, so that's going to be blue. I am given the potential difference, okay, so that's in red, and then I'm asked to work out the resistance. So I could use my triangle, or I can rearrange the equation in my head, but whichever it is, resistance is going to equal V over I. All right, and then I know that V is 14.4, and I know that I is 0.60. And therefore the answer to this question is 24 ohms. Okay, and then looking at the last one, I'm given the resistance, 4 ohms. I'm given the potential difference. I'm being asked to work out the current. Okay, so I equals V over R. If I either use my triangle or just rearrange my equation, I know my voltage is 6.0. I know that my resistance is 4.0. So I now know that my current is 1.5 amps. Okay. Any queries about any of that, please just let me know. Okay, a second equation that we need to know is Q equals IT. So Q is a new thing for us. It represents charge. I we already know because that's the symbol for current. And a lowercase t, and it is a lowercase t, is a symbol for time. So charge, the unit of charge is coulombs. Okay, and we represent that with a C. Okay, we know that current, the unit is amps, and we know the unit of time is seconds. Okay, so I'm going to color code them again just to try and sort of highlight where the values are coming from. So just going to call it, charge is going to be red, current's going to be blue, time is going to be green. So we've got two questions here with different parts. First thing is they give us the current. They're asking us to work out the charge, and they give us time. However, if we just notice with the second one, the time there is in minutes and it's supposed to be in seconds. So we need to convert that into seconds. So that equals 420 seconds. Okay, so that's going to allow us to do part 2. Okay, so let's do one first. So charge Q is going to equal the current, which is 0.72, times time, which is only 4, so that equals 2.88 coulombs. Don't forget your units, please. Part 2, still working out Q, is still the same current. This time we've done it for 420 seconds, so our answer is 302.4 coulombs. Okay. All right, on the second question, oh dear, it's got a number 1, hasn't it? Let's just cross that out. Okay, it's the second question. This time we're being asked to work out the current, but we're given the charge, right? 3,500 coulombs, and again we're given time, and nicely they've given us seconds both times this time. So we can use our triangle, or we can just rearrange the equation, but I equals Q over T, charge over time. So for question 1, part 1, it's going to be 3,500, that's our charge, for our time, which is 9 seconds, which equals 389, that's rounded, amps. And then for part 2, again it's I equals Q over T, same charge, so 3,500. This time the time is much greater, so 200 seconds. That gives us an answer of 17.5 amps. Okay. Okay, so here's the final equation out of the 3 that we've got to learn for year 9. So potential difference equals energy, or work done, divided by charge. So we know what the unit of potential difference is. That is volts. And we know that the unit of energy or work done is joules. And we know that the unit of charge is coulombs. So I'm going to colour code them again. So potential difference in red. Work done, I'm just going to do in blue. Or energy. And then charge, just going to do in green, just to make it clearer. So if we look at the first question, we're given 100 joules, so that's obviously energy or work done. And we're given 10 coulombs, that's clearly charge. We know that potential difference, V equals the energy or work done over the charge. So we know that it's 100 joules divided by 10 coulomb, so it equals 10 volts. Okay. This next one, we are given, the first value we've got is in coulombs, so that's the charge. The next one that we're given is in volts, so that's the potential difference. So we're going to have to rearrange our equation. We're being asked to work out the energy transferred, so we can either use our triangle or just rearrange the original equation, but that is going to be potential difference times charge, okay, which is 230 volts, that's potential difference, times the charge of 10 coulomb, equals 2,300 joules. And then on the last one, we are given the energy, because we can say 100 joules, and we're given the potential difference, which is 100 kilovolts, but we just have to be careful because they've given it to us in kilovolts, so we need to convert that into volts. So 1 kilovolt, so kilo is 1,000, so it's going to be 1,000 volts. Okay, and so we're being asked to work out charge. So charge is going to be, if we either use our triangle or we rearrange the equation, charge equals energy over potential difference. So that equals 100 over 1,000, which is 0.1 coulombs. Okay. If you have any queries or questions about that, again, just drop me a note and we'll sort it out. Okay, so we're going to try and summarize, bring it all together, summarize everything. So current, potential difference, resistance are the 3 key aspects to electricity in year 9. We've got definition, we've got symbol, we've got units. How could we measure them? We're going to have to think about that to do with resistance, because we haven't specifically talked about that, but now that you know one of the equations, you might have an idea about how we can measure resistance, and then how we could either increase any of those or decrease those in a practical sense. What could we do to our circuit to either increase or decrease any of those? So pause the video, have a think, try and have a go at writing what you think would go in these boxes. Try and actually try and remember it yourself, or try and think about it yourself, and then the very final slide will give you a summary of those things. So here's the table filled in. We've got our definitions, we've got our symbols, we've got our units, how to measure. So I just want to highlight one of those how to measures, because the one that we didn't really talk about, but we're going to be talking a bit more about it when we talk about the core practical, which will be a separate video, is we know there's a relationship between resistance, potential difference, and current. We know that because of the equation V equals IR. So we can rearrange that in terms of R. So R is V over I, right? That's just a rearrangement of that equation. And one of the things that we know is we can measure current and we can measure potential difference. We can use that if we put an ammeter in the circuit and if we put a voltmeter in the circuit. So we can do those things. And then if you just look at how we could increase the current, potential difference and resistance, or decrease them, you just look at those tables, what we've got in the table, sorry. If there's anything that isn't clear, if there's anything you want to ask me to sort of explain further, just write it in the Google Doc and I'll sort that one out. But otherwise, that's basically our Year 9 electricity, except for the core practical we have to cover. Now, obviously, we can't physically do the core practical at the moment because of having to be at home, but we can do quite a lot to do with the core practical, and so that will be a future video where we'll look at that a little bit more closely. But until then, I hope this has been useful, and do let me know if you've got any queries or anything. All right, thanks.